Alright, so now let's talk about reaction mechanisms. So reaction mechanisms are a great way to see what the overall reaction looks like. And here's a sort of example of what you may see. So we have NO2 plus NO2 in both in gas form, and then that goes to NO plus NO3. And the most important thing to note is that this says the slow step over here and this says the fast step. If we want to get the overall reaction, or what that overall reaction may look like, then we basically have to look at both sides and see if there's any intermediates. So let me write intermediates. And intermediates are basically molecules that are on both sides. So if I see a molecule on the reactant side and I see the same molecule on the product side, like NO2, then that would be an intermediate. And if I see on the other side of the slow step, I see the product NO3, and I see it on the reactant side, then that's a intermediate form as well. So our intermediates are NO2 and NO3, both in a gas form. So our overall reaction would be NO2 gas plus carbon monoxide, and that would go to, let's see, NO gas form plus CO2. That's our overall reaction. But if the question asks us what is the rate law, so I'm just going to scroll down over here, and it asks us what is the rate law of this reaction. Well, the rate law is always going to be the slow step over here, because the slow step, and I'll write this over here, is our rate determining step. So the slow step determines our rate law. It determines what our rate is going to be. And if we remember rate law, that's rate equals K, and then we only look at the reactant side. So that's NO2, and then brackets, and then NO2 as well. Or what we could do is just NO2 squared, because we have two of them. So NO2 times NO2 would be NO2 squared. And that would be our rate law for this reaction, because it is solely dictated by the slow reaction, because the slow reaction is our rate determining step. Now, what if we have something like this, where the first step over here, so I'll just put step 1 is classified as fast equilibrium, but our step over here, that would be step 2, is classified as slow. Now obviously we have this overall reaction of 2NO2Cl goes to 2NO2 plus Cl2, so the chlorine gas. And how we got there is taking out our intermediates. So this is an intermediate, this was an intermediate, and that's where we got our overall reaction order. But here's something special, because that fast equilibrium, it is, and we're trying to find our rate law, that fast equilibrium basically is necessary in order to find our rate law. So we can't just look straight at our slow step over here. So we can't just say the rate law is NO2 Cl and then brackets Cl2. So we can't say that our rate equals K NO2Cl brackets Cl, because we have an intermediate over here, and that intermediate can't be part of our reaction order or our rate law. So that intermediate can't be part of our rate law, and since it is an intermediate, we need to use this knowledge in order to find the rate law. That might sound a little confusing, but here's what I basically mean. So we know that that chlorine is our intermediate, and that intermediate is seen in the slow step. So in order to get a rate law that doesn't include that intermediate, here's what we do. So NO2 over here, we'll just put that rate law as NO2Cl. And the reverse rate constant would be, I'll just denote it as K to the -1, and then brackets NO2Cl. Okay, now we want to isolate for Cl, so we want to just plug that in there. So all we have to do is just divide this by K -1 NO2 divided to the other side as well, K to the minus 1 NO2, and our Cl would equal K, or that's a bad K, K NO2Cl over K minus 1, which is our rate constant for the reverse reaction, NO2 equals Cl. So now that we know that, I'm just gonna delete this stuff over here. You can pause the video if you want to see this again, but I'm just gonna delete that so we have more space. So that's Cl over there. Now, what about our slow step? So our slow step is K equals, or no, not K, rate equals K2. So this is a different rate constant, and that's why I'm just saying it's K2, just a different rate constant. So brackets NO2Cl and Cl over here. So we have that, we still have that Cl over there, but we know that chlorine, the concentration of chlorine equals the rate constant times NO2Cl over the reverse rate constant times NO2. So all we have to do is just substitute our chlorine inside that slow step over there, that slow rate law that we have over here. So then our rate would equal K2 times K1. I should have put K1 over there. So K2 times K1, and that's NO2Cl parentheses. And since we have two NO2Cls, we can just put that as squared, and that's K negative 1 NO2. And we can just say that these K's cancel out. So this is our rate. Our rate is NO2Cl squared over NO2, and that is our rate law for this reaction. Now just to review what we just did, so this is only when it applies to fast equilibrium. And we have the intermediate, so we can't just straight up say that our K equals NO2Cl and times chlorine, because we have that intermediate and we can't have an intermediate in our rate law. So all we really did is go to step 1, and we sort of found the rate law for step 1. So step 1 was NO2Cl, it was K1, and then times, we had that K negative 1 over here. So this was, if I wanted to write this again, it would be K1 over here, and then bracket again, bracket, and this was, and it's a little hard to put this in, but that is the rate constant for the reverse reaction. And all we did is divide or move this NO2 to the other side, which is what formed this rate law over here, and that equals Cl, that equals our concentration of chlorine. And after that, we just wrote our rate law for the slow step, which we're only using reactants. So with the rate laws, we're only using the reactants in this case, and we have that Cl over here, so we just plug that in or substitute it in, and we had two NO2Cls, and we still have that NO2 on the bottom. So this was our rate over here.